Sebastian and Katie gave a lot of motivation for what I'm going to talk about today. So we'll consider M, which will always be I should say this is Kim and Nuez Gonzalez, both of whom are in kiosks. So we'll let M be a compact manifold. So this will always assume that it's connected, although this is not a major assumption, and it possibly has a boundary. And we're going to think about the following following huge group, homeo of M, and in particular, its first order theory. So I'll explain what this means in just a moment. Okay. So what I'd like to understand is, in some sense, to what degree does homeo of M as an abstract group determine M? Okay. So Katie already even stated for us a motivating basic result in 1963. I'll just restate it just so that we can get back on the same page. This is a theorem due to Whittaker from 1963. And so what this theorem says is that if, for compact manifolds M and N, then if you have a isomorphism of groups, abstract isomorphism of groups from homeo of M to homeo of N, then this implies that there exists an actual homeomorphism between M and N inducing the such that for all G in homeo of M, we have that phi of G is equal to right. Whoops. Right. It's F G F equals. So let's do it by conjugation by okay, great. So I said at the very first thing I said was that you want to know to what degree homeo of M determines M. Well, that's kind of an answer right there. But right, so homeo of M is way too big to for this some sort of data like, okay, here's an isomorphism between two homeomorphism groups. That's just way too much data to be given. Like I don't feel like I understand such a thing. I wouldn't be able to write down such a thing. I don't think anyone could. These groups are very complicated. So what I'd like is some sort of finitary way of understanding Whittaker's theorem. So is there some way of understanding homeo of M in some way that I can write down, some way that I can hold in my hand, which determines M already? And so for that, we're going to consider the first order theory of homeo of M. So that's something that I'll write by theory of homeo of M. So I mean this in the sense of standard model theory. So again, what does this mean? Okay, so the elements in the theory of homeo of M are simply formal sentences in the language of group theory, which are true inside of this group, homeo of M. So basically, right, so the parts of what I just said are that we have this language, which is the language of groups, okay, and it consists of two non-logical symbols. So non-logical symbols are this binary operation, which is interpreted as group multiplication, okay, and this constant, one, which is interpreted as the identity element. Okay, and then you have, so these are the non-logical symbols, and then you have the logical symbols which are present in every language when you talk about the first order theory of some structure, and these are things like and, or, not, implies, and so all right, equal. That's there's some discussion to be had about whether or not that's a logical symbol or not. Okay, and so from these pieces, you have access to you can talk about structures which are given interpretations of this binary operation and this identity element. And you talk about specific elements inside of such a structure by access to variables, which you have a countable number. So, right, some collection here, xi, variables. And so then you construct these formulae out of this language, and then in addition to these logical symbols that are written here, you have quantifiers, which are for all, and there exists. And so then the first order in this name simply limits the scope of these quantifiers. So this quantifier will, for instance, for all, let's say for all x, something is true. And first order says that x is only allowed to take values as elements in the underlying structure and not as, for instance, subsets of this Cartesian product or something like that. So you can quantify the word elements in a group but not say homomorphisms or subgroups. Okay. So to talk about in detail, so precise definitions of everything that I said here in terms of model theory would eat up all my time and more. So maybe I'll just give one example of some sentence, which means something meaningful in group theory, which may or may not be in the theory of some group. So, for instance, if you wanted to say that this group is abelian, then you might say something like for all x, for all y, x times y is equal to y times x. So this will be an element in the theory of group G if and only if G is abelian. So, okay, so I mean, I think it's maybe the details are fuzzy, but the point is that if I consider the first order theory of some group in the language of group theory, I'm saying I'm looking at things which are true in that group with when I'm allowed to quantify for their elements. So one bit of notation. So this inclusion of some sentence in the theory of a group is oftentimes also written as G models a particular sentence. It's called phi. So we write G models phi if and only if phi is in the theory of that. Okay, so that's all in terms of a crash course on model theory. Okay, so of course you may have guessed already that the reason I'm bringing up the first order theory of M is because I want to understand this theorem from the point of view of things that I can actually write down, like sentences in the language of grouping. Okay, so that's exactly right. So before I state any actual results, I'll tell a bit of a funny little history. So one person who spent a lot of their life thinking about automorphisms of structures and the relationship between automorphisms structures and logic of various orders was this person, Rubin, who is unfortunately no longer with us, but in a 1987 paper that appeared in the Transactions of the American Mathematical Society, there appears the following claim that, so assume V is equal to L. So I'll explain what that means in just a second. Then if M and N are arbitrary manifolds with homeo of M elementarily equivalent to homeo of N. So I'll explain what that means in just a second. Also, then M and N are homeomorphic as manifolds. Okay, so what's going on here? So this statement just means that the theory of homeo of M is equal to the theory of homeo of N. That means that every single statement that you can make in the first order language of groups about the homeomorphism group of M is also true in N and vice versa. Okay. So in general, this is a much weaker condition than isomorphism of groups. For instance, there's a theorem of Sella, which says that if you take a free group on 2 generators and a free group on 3 generators, then they're elementarily equivalent, but they're not isomorphic as groups. And then this thing, V is equal to L, is a certain, this is also known as Gödel constructibility. So this is an assumption about the type of set theory that you use. And so, yes.
Sorry, I think you said this is kind of a throwaway comment, but it just struck me. So there are no first order statements that you can make about the free group on it, or they're also not true about the free group on 3 letters.
Yeah, 2 and 3, but yes, yeah, but that's true. Yeah, it's very so. If you try and start playing around with like things that are natural for group theorists to say about groups, you find that they're actually quite difficult to express in terms of first order theory. Like even defining finite index subgroups is not easy. And like forget talking about like this subgroup, if this group is generated by like n elements, it's just not possible. I mean, it may be possible in some groups, but not in the free group. So this, right? So this is an assumption about set theory. So right, if in this sort of von Neumann conception of set theory, right, you start with the empty set, and then you start building up sets by taking the power set over and over again. Right? And what Gödel says is like, well, what if you assume that the only sets that you're allowed to build when you take the power set are the ones that are defined by actual first order formulae? Okay, so it's called constructible sets. And he says, well, if you assume something like that, then I can like prove the axiom of choice, and I can prove the continuum hypothesis. So this is some sort of extension of usual ZFC, which I think most theorists, set theorists agree is too strong. Okay, so anyway, so Rubin claimed that he could prove this, and no paper by the name of the one that he said would ever appeared in the literature, and no proof of a theorem, anything resembling this ever appeared. And this was more than 30 years ago now. Probably because the statement is incorrect. So, for instance, you have that like homeo of your closed interval 0, 1, and homeo of the open interval are isomorphic as groups, but the underlying manifolds are not. So maybe there's some sort of modification that might help here. And I really don't know what he was trying to do here with the set theory. So I mean, there's this theorem of Miklos Aitai from the late 70s that says if you assume like V is equal to L, then you can prove that two structures are second order equivalent. That means that you're allowed to quantify over subsets. Then you can promote that to isomorphism. But that's only for countable structures, and there are all sorts of issues that I don't know how he was going to get around. But anyway, so that's the history. And yeah, so then the theorem that we're going to talk about is that for M compact, there exists a sentence, P sub M, in theory of homeo of M, such that for all N compact, we have that homeo of N models P sub M if and only if M and N are homeomorphic as manifolds. So in plain English, I guess this sentence is saying that I am homeomorphic to M. And right, so I'll note a few small things that can be done, right? So you can actually replace homeo here by homeo 0, if you like. And so you only need to consider the identity component of this group. And if you have a certain nice measure, so what we call Ox-Tobey-Ulam measures. So what that should be is a Borel probability measure that assigns positive measure to every open set, has no atoms, and which gives measure 0 to the boundary. And if you look at groups of homeomorphisms that preserve an Ox-Tobey-Ulam measure, then the same result is true. And also, you can also restrict the identity component of such a group. So those are all very, very large groups, except for maybe like the measure preserving homeomorphisms of the interval, which is very, very small. So you can pretend it's just like a Lebesgue measure. So if you preserve a Lebesgue measure, then you have to be isometry, and there aren't that many such homeomorphisms. Okay. Great. So right, so that's the generalization of Whittaker's theorem. That's sort of in principle possible to write down. So I'll also note that when we write down this, or when we prove the existence of this sentence P sub M, the proof is completely constructive. And so if you had a lot of paper, you could write it down. You can write it down explicitly, I think, for one-dimensional manifolds, but that's because one-dimensional manifolds are somehow special. I wouldn't want to do it for even the two-dimensional sphere, but if you could, if you wanted to. Great. So let's move on. And let me so let me say why you might believe that a theorem like this is true. So basically what you need to do is you need to be able to read off from just the group theory of the homeomorphism group of a manifold that you are homeomorphic to a particular manifold. So where does one start? Well, so Christian Rosendahl pointed out to me the following result of Cheeger and Kister, which comes to the rescue, though maybe not immediately in an obvious way. So Cheeger and Kister proved this theorem that so if you look at compact topological manifolds up to homeomorphism, that this is countable, the set of compact topological manifolds. Yeah. So by the way, I mean, this theorem also gives another. This implicitly says the same thing because there are only countably many sentences in the language of group theory with countably many variables. But a priori, it's not clear how this might help you. But the content of the Cheever-Kister theorem is in the guts of the of the proof of what they need to execute in order to be able to prove this theorem. So what they have is the following. So they start with a compact manifold M, and they start with some arbitrary embedding of M into L-dimensional Euclidean space. So then they say, okay, well, this by itself is somehow dependent on M. So it would be nice to think about such embeddings in terms of just some sort of nice thing that we can talk about inside of some Euclidean space. So this is an N manifold, so I'll write that implicitly. And we can cover M by finitely many Euclidean balls. Okay. So M is equal to a union equals 1 to k of, say, maybe B sub I, where we have these maps called, I'm overusing phi, but whatever. Okay, phi sub I is some homeomorphism from the ball of radius 1 sitting inside of Rn with B sub I. Okay. And then if we consider, I'll name this map iota sub m, then we can consider this map that we get from the ball of radius 1, which is now something that doesn't know what m is anymore, which is, we get this map, I'll call it big phi sub m, which is defined to be iota sub m, composed with the product of the phi sub i's. So this is to r to the k times l. Okay. So you can, whenever you have a cover of your manifold by balls, okay, and an embedding of that manifold into RL, then you get this map phi sub m. Okay. It depends on this embedding iota and the PIs, but I'll suppress that from the notation. Okay. And so the crucial fact that Cheever and Kister prove, which uses like this difficult work of Edwards and Kirby, is that if N is also compact, an N manifold covered by K balls, so somehow a similar data to what we have here, and if the corresponding maps phi sub m and phi sub n are close enough, so there's to say, I mean, these are simply maps from the ball into some Euclidean space, so you just need these to be close enough in like the uniform metric, for instance. This will imply that M and N are homeomorphic as manifolds. So that's sort of the crucial thing that Cheever and Kister prove. Once you know this, it's not that difficult to imagine how they conclude that there are only countably many compact topological manifolds up to homeomorphism. So what might you do? You say, okay, so if there are uncountably many, then there are uncountably many in a given dimension. And then among those, there are countably many that are covered by, say, I don't know, 10 balls. And so then you appeal to some sort of separability properties of the space of embeddings of a ball of radius 1 into some fixed dimensional Euclidean space to say, well, if you have this net there that you can extract some more convergent subsequence, and then you have, so then you can assume that if you had uncountably many different homeomorphism types, and there are some for which these maps phi sub m and phi sub n are very, very close to each other. So then you conclude that that sequence is actually stable after finitely many terms in terms of homeomorphism. Okay. So that's how this theorem works. Okay, well, how might you relate this to what we want to prove? Well, once you know this crucial Cheever-Kister lemma, then what you need to do is you need to be able to express the statement that, okay, phi sub m and phi sub n are somehow close as maps from the unit ball into some Euclidean space. But that's, I guess, where the challenge is, because the homeo of M is just a group. All you have access to are group multiplication and the identity element. And you can talk about, finitely many elements at one time. And so how do you talk about things like covered by balls or continuous function to Rm? So that's where the rest of the work goes into proving this result. So I guess the mantra that one could say is that the first order group theory of the homeomorphism group of a manifold is very expressive. And if I hope that near the end of the talk, I'll be able to show you how almost absurdly expressive it is. It has too much power almost to be reasonable. So, I mean, right? So things like you might say, okay, well, like, can you check? Can you feed a homeomorphism group to a computer and say, like, is this homeomorphism group the homeomorphism group the 5 sphere or something like this? And the answer is probably not. Even if you just start sort of enumerating statements that are true in homeo of the 5 spheres, simply because this theory, the theory of the homeomorphism group of a manifold, is not decidable. Like, there's simply no algorithm which will enumerate the true statements. So I'll explain that in just a moment. So the first order group theory of the homeomorphism of M is very expressive. It interprets many things. So I'll list and comment on some of them. So the first thing that you start with is just you have the underlying group structure. That's just what you're given. So the next thing that you can do is you can take the group structure and you can recover not all of immediately, but a large part of the topology of the underlying manifold. And so what you can reconstruct is the algebra of regular open sets. So I guess with the homeo action. So let me explain what some of these things are. So an open set in a topological space is regular if it is equal to the interior of its closure. And regular open sets are nice because they form a Boolean algebra, as opposed to simply something called a hating algebra, which is true for general open sets. And so you have the notion of a meet and a join, a complement, a sup, an inf, and those always exist. And what's more, every regular open set of M is given by something that we call the extended support of some group element. And so what I mean here by this arrow is, I mean that there's a uniform interpretation of the algebra of regular open sets inside of the homeomorphism group of a manifold. That means that I can take the homeomorphisms of M, and I can impose an equivalence relation on them, and that equivalence relation does not depend on which manifold I'm working in. And the equivalence classes of that equivalence relation are in natural bijection with the regular open sets of M. And basically the correspondence is like this. You take the equivalence class of G, some homeomorphism G is basically we write extended support of G. So the support of G is what we call the support is the open support. So this is just the X is such that Gx is not equal to X, and then the extended support of G is the interior of the closure of the support. Okay, so the fact that you could reconstruct the regular open sets from the underlying group of homeomorphisms, this was well known. This was known to Rubin, many others who were working in this field. And you might be like, well, this is already a lot of the topology of M. Maybe this is enough. And I'll say that my co-authors and I, we spent a lot of time trying to just use this amount of data, just the regular open sets and the homeomorphism action on them to reconstruct the topology of a manifold. And it's really hard. And we could get these things like, okay, if you know that M and N are like surfaces, and their homeomorphism groups are elementarily equivalent, you can like prove that the surfaces were homomorphic to each other. And we think we could do it like the three manifolds, but it was, we're not getting very far, especially because some nice things that you would hope to be able to say about regular open sets, like this regular open set is homeomorphic to a ball. Like, how do you even begin to say something like that? You could be like, well, maybe U is a ball. If like for your favorite regular open set V, you can find a homeomorphism that takes U into the interior of V or something. But then there's nothing to stop U from having holes in it and stuff like that. And that's just a two-dimensional abstraction. If this is in like R17, like I have no idea what's just crazy things might be happening there. So this is unfortunately not enough right there, but you can do a lot more. So you can uniformly interpret second order arithmetic. That is to say, you can use the regular open sets and the homeomorphism group action on the regular open sets to build in some way it's completely uniform, not depending on what M is, a copy of the natural numbers and a way to add them, multiply them, and compare them in terms of the order. And also, you can talk about subsets of the natural numbers in a natural way. So I won't belabor how that works. Suffice it to say that if you just consider the group theory of homeomorphisms of M, it knows a lot already. Just the group theory can be used to recover second order arithmetic. So you can talk about the real numbers. You can talk about Rn. You can talk about functions from the real numbers from Rn to Rn for different values of N. You can talk about continuity. You can talk about a lot of things. So then the last thing you need to do is then to interpret parameterized balls. So what these are exactly what they sound like. So these are like actual copies of the ball of radius 1 identified as regular open sets, but also the coordinates given. So you can talk about like, okay, this is the point corresponding to this rational point inside of Rn, inside of this ball. So the way one does that is okay, you can use the machinery that you need to construct to understand second order arithmetic to construct three continuous actions of Rn on the n manifold, which are supported inside of a regular open set. And then you truncate it somewhere, you get these nicely embedded copies of Euclidean balls. So once you have all that, you basically explained all the pieces that you need to say, like, okay, here is like, okay, so if I start with n, then I just choose phi sub n arbitrarily. So I just take some embedding into RL, some covering by balls. And then Shiger and Kister says there is some positive epsilon for which whenever some phi sub n is close enough, then n and m are automatically homeomorphic to each other. So then I can write down some finite approximation to phi sub m, maybe to find some sufficiently dense finite subset of the manifold. And then say, okay, I let the sentence lowercase phi sub m be. I admit a function of the form phi sub n that is within epsilon, in the uniform distance from this fixed one that m has. And that's all that one needs to prove the theorem. So in the remaining time, let me talk about a little bit more about how expressive the theory of homeomorphisms of n is. So one thing I'll remark, so we have this notion of elementary equivalence, right? So this in particular proves that if two homeomorphism groups are elementarily equivalent, the manifolds then the homeomorphisms the manifolds are homeomorphic to each other. We actually have something stronger here. There's actually just one sentence that nails down the homeomorphism type of a particular manifold. And so this has the very catchy name of being homeomorphism groups of manifolds are quasi-finitely axiomatizable. This falls off the tongue. All right. So what else can you do with homeomorphism groups and first order logic? Well, it turns out that you can say almost anything that you might want to be able to say about a manifold. So here's a sample results. Here's a proposition. So let sigma be an arbitrary closed surface. So two-dimensional manifold. So there exists a sentence, we'll call it psi sub lin, which is independent of sigma, such that homeo sigma models psi sub lin if and only if the mapping class group of sigma is linear as a group. So it's a faithful linear representation into some finite dimensional general real union. Or another thing you might do is so there exists a sentence psi sub t such that homeo of S1 models psi sub t if and only if there exists an infinite finitely generated subgroup of homeo of S1 with property T, or some other thing that you might be able to do. How much time do I have? 2 minutes, perfect. So there's this, I mean, this question is really outstanding, whether or not there exists such a group. Is an outstanding case of the Zimmer conjecture in one dimension. And the Zimmer conjecture for homeomorphism groups of manifolds is generally open. So for example, maybe want to know, so does SL4Z, for instance, act on homeomorphisms? Maybe asking to find an index subgroup on S2. Okay, so we know from the work of Brown and Fisher and Hurtado that if you assume C2 diffeomorphisms, then the answer is no. And also if you assume that there exists an invariant volume formula, C1 is even enough to be an obstruction. But we don't know, I think, in general for homeomorphisms. Right, so then there exists like a sentence. So there exists a psi SL4 S2, for instance, that's, or in fact, you can make it for sigma. Sigma is just some arbitrary surface, such that homeo of sigma models psi SL4 sigma. Actually, I'll since this doesn't depend on sigma, I'll erase it from the notation. If and only if SL4Z, or even some finite index subgroup, sits inside of homeo of sigma. So as I said, I mean, this step here in like understanding the first order theory of the homeomorphism of the manifold is this carries a lot of weight. Right? So like Gödel's incompleteness theorem that says that any theory that contains already first order arithmetic, or at least like piano arithmetic, then you're not going to be, then the theory is not decidable. So there's no way we're going to sort of just like write down true statements in homeomorphism, decide if any of these particular sentences hold in any homeomorphism. But at least you can write down equivalent statements which are just purely group theoretic statements in these huge groups. So I'll stop there.
Questions? I just had a quick question just to clarify something. I'm not sure if you talked about it, but what's the equivalence relation again, like for up there where we had like T?
Oh yeah, I didn't really spell out what it is. Right. So so writing it down is a matter of a little bit of annoying bookkeeping, but what you can basically think of is that, okay, so like two group elements are going to have the same support if you commute with the right things. Yeah. So that's a very broad strokes way of saying, like, to get it exactly right, it's a little more annoying, not much.
Okay, if there are no other questions, we conclude this session. So we meet tomorrow at 9:30 or earlier if you're hungry. And thanks, Thomas, again.